You know, there are some laws in physics that just feel unshakable. They're the bedrock principles we all learn from day one. And the biggest one of all? The law of conservation of energy, right? Energy can't be created or destroyed. It just changes form. It's simple, it's elegant, and well, it's not actually true.
All right, let's really get into this. Picture it. You're out in deep space, and you throw a rock. Basic physics says it should just keep going forever at the same speed. But here's the catch. Our universe is expanding. Space itself is stretching. And over these just immense distances in time, that stretching actually slows the rock down relative to everything else. So, what happened to all that kinetic energy? Where'd it go?
And this isn't just some weird thought experiment. This is happening right now, all around us. Take a photon of light from right after the Big Bang. It travels for billions of years to get to us. But the whole time, the universe is expanding, stretching that photon's wavelength out. It goes from being visible light to a super low-energy microwave, losing almost all its energy. So I'll ask again, where did that energy go? It seems like it just vanished.
Now this whole problem, this apparent violation of a fundamental law of physics, isn't new. It actually goes back more than 100 years, and it completely stumped the one person whose theory started it all, Albert Einstein. So check this out. It's 1915, and Einstein is rolling out his masterpiece, the general theory of relativity. But almost immediately, this huge problem pops up. Even another brilliant mind, the mathematician David Hilbert, couldn't figure it out. The equations for general relativity, which describe gravity as the curvature of spacetime, just didn't seem to account for energy conservation. The math wasn't adding up. I mean, this was a serious crisis. You've got the greatest minds on the planet staring at a theory that explains the entire cosmos, but it looks like it breaks the most fundamental rule in the book. The solution, it turns out, wouldn't come from Einstein. It came from a brilliant, unpaid, and criminally underappreciated mathematician who was about to change physics forever.
Her name was Emmy Noether, and the key she used to unlock this whole mess was a concept that is just profoundly beautiful and powerful: symmetry.
And to really get how amazing her breakthrough was, you have to understand what she was up against. Emmy Noether was a flat-out genius. But because she was a woman in early 20th century Germany, she wasn't even allowed to officially enroll in university. The academic senate literally said allowing her in would overthrow all academic order. But she kept going, eventually got her PhD, and worked for years without pay. Her story is just one of pure brilliance winning out against impossible odds.
So what was this secret weapon of hers? Symmetry. And really, it's a simple idea. A symmetry is just anything you can do to an object that leaves it looking exactly the same. You know, like if you rotate an equilateral triangle by 120 degrees, it looks identical. That rotation? That's a symmetry. But Noether was interested in a very special kind of symmetry. Not the discrete kind, like with the triangle, where you only have a few specific steps. She focused on continuous symmetries. Think about the laws of physics themselves. You can do an experiment right now, or in 5 seconds, or 5.123 seconds. You can move your labo foot to the left, or just a tiny fraction of an inch. Because you can make these changes by any amount, no matter how small, they're continuous. And this, as Noether discovered, is the key to, well, everything. And this is where she made one of the most incredible connections in the history of science. She realized that this abstract mathematical idea, continuous symmetry, was directly, fundamentally, and unshakably tied to the physical laws of conservation. This is the heart of her famous theorem, and it's just so powerful. It's not a coincidence that things like momentum and energy are conserved. It's a mathematical necessity. She proved that for every single continuous symmetry you find in the laws of physics, there has to be a corresponding quantity that is conserved, period.
Let's just break down the big three. If the laws of physics are the same for you here as they are for someone in another galaxy, that's symmetry in space. And boom, that gives us conservation of momentum. If the laws are the same no matter which way you're facing, that's rotational symmetry. And that's where conservation of angular momentum comes from. And now for the big one. If the laws of physics are the same today as they were yesterday and as they'll be tomorrow, that is symmetry in time. And that is the reason we have conservation of energy. So Noether's law is perfect. It gives us this beautiful direct link, time symmetry equals energy conservation. But that forces us to ask a really uncomfortable question about the actual universe we live in. So let's just ask it straight up. Is our universe really the same today as it was 13 billion years ago?
Are the background conditions for every experiment you could possibly run truly identical across all of cosmic time?
The evidence is just overwhelming. We've known since the 1920s that the universe is expanding. All the galaxies are flying away from each other. And then, in the 1990s, we found out that the expansion is actually speeding up. Our universe is anything but static.
So the conclusion is totally inescapable. A universe that's expanding and accelerating is fundamentally different from one moment to the next. The density, the temperature, the very fabric of space-time, it's all changing. On the cosmic scale, time symmetry is broken, and according to Noether's perfect law, if the symmetry is broken, then the conservation law has to be broken too.
Let's go all the way back to that photon we talked about. When it first started its journey in that hot, dense, early universe, it was a high-energy particle of visible light. But as it flew through space that was stretching year after year for billions of years, its energy just leaked away. It bled out into the expansion of the universe itself.
And that is the jaw-dropping answer to our whole mystery. On the grandest scales of space and time, energy is not conserved. It doesn't turn into something else, it just goes away. And this isn't some mistake in the laws of physics, it's the revelation that the very condition required for that law to hold, perfect time symmetry, simply doesn't apply to our universe.
Okay, so that solves the mystery of the rock and the photon. But wait a minute. If energy isn't conserved across the whole universe, why does it work so perfectly in every single lab experiment we've ever done here on Earth? Well, it turns out the rest of Noether's work also solved Einstein's original problem. Noether gave us a fantastic way to think about this. Imagine energy is like water flowing through pipes, and the pipes are space-time. Now, in any small, local section, say our solar system over a couple hundred years, the pipe is perfectly sealed. Energy is conserved. Water in equals water out. But general relativity says space-time is curved. So when you try to connect these pipes over huge cosmic distances, that curvature means they don't line up perfectly. Tiny little cracks appear between the sections, and on that massive global scale, energy can leak out. This was the absolute genius of her solution. Noether proved that general relativity demands that energy is conserved locally, but it actually allows it to not be conserved globally. This leaky conservation wasn't a bug in Einstein's theory. It was a fundamental feature. She single-handedly solved the problem that had the greatest minds in physics totally stumped. And Einstein himself knew it. Years later, he wrote a letter to the New York Times about her, calling her the most significant creative mathematical genius thus far produced since the higher education of women began. I mean, what a tribute to the woman who fixed his theory. And her impact, it just exploded from there. This central idea that symmetries dictate physical laws became the guiding light for basically all of modern physics. It's what led us to discover fundamental particles like quarks and the Higgs boson. It helped us understand the fundamental forces of nature and even where mass itself comes from.
Emmy Noether's story and the real story of energy conservation is just such a powerful reminder that in science, even the rules we think are absolute can have some serious fine print. It shows that we have to keep questioning everything. Which really leaves us with one final thought to chew on. If a law this fundamental can be broken, what other unshakable truths are out there just waiting for the next Emmy Noether to come along and rewrite them completely?